All right, so let's look at the moment of inertia. As we said previously, inertia is a resistance to the change of state of motion. And for the linear motion, which is a motion along a line, this inertia is related to the mass. The more of the mass, the larger of the inertia, which will make it harder to move or harder to change its state of motion. So, and we don't have a unit or a measure for the inertia for the linear motion. However, for the rotation, we do have a symbol that we use to represent the moment of inertia, and we have an equation to calculate the quantity of that. So it's more like a mass in rotation. So let's look at how we define that. So I want to start with the moment of inertia. The moment of inertia we use a symbol I to represent it, which represent like inertia. It is an if you have an object and this object doesn't have to be like a one piece. If this object composed by smaller components, such as you have several different shapes of the object connect together, or you have a big piece of the object, you can cut it into the smaller piece. Then that can help us to calculate this moment of inertia. So if I have several of them, and each one of them has a certain amount of a mass, I just use a symbol m sub I to represent the mass of the first one or second one, etc., etc. And it also, they are rotated, and their distance and you're doing a rotation, and when you rotate, you have a fixed axis to describe how the things is rotating around. And we define the Ri will be the distance from the object away from the axis of rotation. If this is the case, then we can write the equation to calculate what is the moment of inertia of this object. So, and that is, this I here is simply equal to the summation mi times the Ri square. Last time I only use Ri, which is wrong. It should be the square. So the distance square is the just distance. So mi times Ri. And if you have the I could be from 1 to n, if you have n objects. Only have one, you just simply use the mass times how much of the distance of this mass away from the center of the rotation. Now you might feel weird, if you have a disk, it's no way that you can actually know where the distance from the object to the center of the rotation, right? That's why if we want to calculate this, we have to cut it into smaller pieces and to sum them together to figure it out. I'm going to show you one example, but we are not going to derive those equations, how you actually ends up getting the I for a certain kind of shape. I also wanted to point out the unit for the moment of inertia is simply just the kg times meter square. That's the unit of I. Okay, it's just simply based on the equation. Mass is in kilogram, and the r, the distance, is the meter. It probably is the best that we can show you like an example. So I'm going to give you a quick, simple example over here, which is the same example I showed you previously, but because I said it wrong, I wanted to make the correct calculation over here. So let's say I have an axis over here, and I have a very small rod connect to a piece of a mass, and just say this mass is a very small dot, and this mass is concentrated at this point, which is 4 kilograms. The distance from this mass to the axis is simply equal to 4 meters, and it's rotating around this axis. And then based on the equation that we just told you, you can calculate the moment of inertia for this case, right? So what is the moment of inertia? Well, I only have a one piece of the element, so I don't need to do any of the summation. There will be simply just the mass times the r squared, where the mass is 4 kilogram, r is 4 meter. You put a square, and that will give you the moment of inertia in this case, which will be 64 kg meter square. That's used this similar way to find the moment of inertia. Again, this is my central rotation, but my object is not all concentrated at the edge. It actually separates into like the smaller pieces, and it happened to separate by the 4 different smaller pieces, and each one of them are just like a dot. Okay, and each one of them is 1 kilogram. So each one of them the same mass, but the distance, this one is going to be 1 meter, this one is going to give you 2 meter, and this one is going to give you 3 meter, and this one here is going to give you 4 meter. So if we want to calculate the moment of inertia in this case, this moment of inertia will be equal to a summation of mi, ri, where I is equal to 1 to 4 because I have 4 different elements. And then you can simply multiply them together. The first one is 1 kilogram times, that's from the outside to the inwards, and that will be 4 meter squared, plus 1 kilogram times 3 meter squared, plus 1 kilogram times 2 meter squared, plus 1 kilogram 1 meter squared. So you sum them together. This is simply just 1 kilogram multiplied with 4 squared will be 16 meters squared, plus 9 meters squared, plus 4 meters squared, plus 1 meter squared. And therefore, if you sum all these together, you got the value, which is 30 kilogram meter squared. All right, so this is an important idea. If you have like a 2 different distribution of the mass, even though the total mass is the same, but because the distribution of the mass is different, you got different rotational inertia or the moment of the inertia. One is larger, one is smaller. So what does that mean, a larger I or smaller I? What does that represent in physically? What does that tell you? Well, inertia represents the resistance to change of the state of motion. The larger I meaning is harder to change the state of motion. If you wanted to rotate it and starting from 0, larger I meaning is harder to make it rotate. So and this one in this case is a smaller I, so easier to rotate. And you can also think about this as a change of the rotation. If things start rotating and you want to stop it, and which one is easier to stop? Well, the smaller eye, meaning is easier to stop it, where the larger eye will be harder to stop it. So that's the moment inertia. Now, in the textbook, there's a table 8.1, which is kind of important because when you have an object, it doesn't have to be simply just a small point of the mass. You could have an object such as like a shell shape of the cylinder, or you can have a solid cylinder, or another way you can look at that is like a hollow hoop or a solid disk. So these two, one is hollow and one is solid. This one is solid, this one is hollow. In the lab that you're going to do, which you are going to use a hollow hoop, well, more like this one here. And you're also going to do a solid disk. So you are going to look at these two situations in the lab. And you were also going to see the equation, where the equation that will give you, one is this equation, and the other one is going to be this equation. So for different shape, without derive how this came out, is that you simply just use the equation to find out the moment of inertia for the particular shape. Second thing I wanted to tell you is, if you have a three-dimensional object such as this one here, you can see they have I for two different scenarios. What does these two scenario means? Both these two are the same shape. However, for this one here is rotating about the center of the cylinder, where this one here is rotating about the length of the cylinder. So this is where it's rotating about. So if you are rotating an object with a different orientation, then the moment of inertia will be different, because the shape, not only the mass, will matter in the rotational inertia. And in the exam, we will give you the formula. You just need to know how to use those formula. Mass is easy. I think the most possible way you will make mistake is simply just radius. For this case, since it's rotating about the length is going to be part of the inertial calculation as well. Okay, so we will use this kind of table when we do the calculation. Now let's look at how we can use this idea to do the calculation with an example over here. It's very similar to the previous example. We wanted to know if you have a dumbbell with a rod connect of these two. And the distance of these two are separated by 2.4 meters. We're looking at these like two different cases. The first case is it's rotating about this one here. It's rotating about the center. The other one, we are rotating about one of the sphere. Okay, so one is rotating about the center. The other one is rotating about one of the dumbbell. And we want to find what is the inertia. Okay, so let's look at the first one. The first one, the axis is at the center, so the distance for each one of them is just half of the 2.4 is 1.2. Therefore, if you want to find the moment of the inertia of this one here, or rotational inertia, this one here is going to be equal to the summation MIRI, where I is equal to 1 to 2. You only have two objects. So the first mass and second mass, they're simply just equal. So I'm going to just say this would be M1 R1 plus M2 R2. What is the M1? Well, 50 kilogram. R1 is 1.2 meter. And same thing for the second one. They are identical. If they're not, just use whatever the value is given. Now, you sum these together, this is going to be equal to 144 kg a meter square. But if you're rotating about one of the sphere, now this one is going to be different. This one, you can still using the same way to find your total moment of inertia for two different objects. However, if you look at the first one, let's say the first one is on the left, it's still 50 kilogram. But what is the R? Well, the R is just right at the center of the rotation, so the R is simply equal to 0. Well, this should be square. Oh, I always forgot this should be square. Square. Okay. And what about the second one? The second one is 50 kilogram times, instead of the 1.2, this will be 2.4 meters square. And you calculate this will be equal to 288 kg meter square. Okay, same object, but if you're rotating about a different point, then you will have a different moment of inertia. Now, as we said, which one is easier to change is rotational motion? Which one is easier to change, to make it rotate? The larger of the eye, the harder to rotate. So if you rotate a dumbbell and make it rotate around the center, which is easier than you make it rotate around one of the end dumbbell. And that's what this one is telling you. Okay, we'll go back to this problem a little bit once we introduce the energy. Now, energy, because rotation also have a motion, it will be very similar to the linear motion. We can also have a kinetic energy. Kinetic energy is always related to how it moves. We have two different kinds of motion. We have a kinetic motion. We have a translational motion. We have a rotational motion. The translational meaning everything is moving along a line or a curve. Then how do you see this? Well, oops. So the way we define this translational motion is, we found out if any line inside of an object they keep at the same direction. During the motion. And if this is the case, then you have what we call a translational motion. So an object could be a big object, could be a small object. For example, if you have an object like this, a rectangular, or make it a little bit different. Now, this is the shape of the object. And let's say this object will move, and this is it's moving in this way. Right. Now, any line inside of the object, meaning if I look at this line here, when this one is moving, if it doesn't rotate, meaning it doesn't matter where it moves, it's always going to keep the same orientation. right? And this line here is going to be the same as, is going to have the same direction during the motion. It doesn't change. This line doesn't rotate to a new direction. If this object rotates, then this line will change its direction. So because we don't change the direction of this line, that simply tell you this is going to be a translational motion. With the rotation, the line will rotate. It's going to rotate around one of the axes. So this is what the difference between the translational and the kinetic and the rotational. With the translational, we have the equation that we showed you before, which is 1/2 mv squared. Rotation is very similar to translation, is 1/2 I omega squared. Now, how do we get this equation? How can we represent that in this way? Well, actually, if you look at these two, it is really just coming out from a relationship between the V and the omega. If you have a translational motion and if you have a rotational motion and at any moment of the object is actually also going to have a tangential motion. It's the motion which is on the edge, which is now rotating. For example, this is a disk. This is the best way to look at the motion. This is the disk. And one of the objects around this disk at here is going to rotate. So it's going to rotate in this way. When it's rotating, we know there's an omega, which represents the rotational motion. However, if you look at that moment, it also going to have a direction of the motion, which is what we represent as v of t, which is the tangential velocity at that point. And if we know how this one is rotating, this should be in the radian per second. And if we also know the position of the object, meaning how much this one is away from the distance of the center of the axis of the rotation, then we can find out this tangential velocity. This will be simply equal to r times omega. Which means if this is like a disk is rotating, the further away from the center, the faster of the speed of the object has to move. And which means if you are further away and you want to keep the same pace as the object is rotating, you're going to walk more of the distance, and that's why your VT is going to be larger. If you are further away from the center, the R will be larger, then V sub T will be larger. Omega is going to be the same if you have the object along the same line on this disk, and because they rotate at the same time, otherwise the whole object will be twisted. So if the disk rotating at the same time, any point along the line from the center to the edge is going to rotate at the same speed. So this equation, this is a very important equation. You have to know that the tangential velocity is equal to the r, which is the distance away from the center of the axis of the rotation, times the omega, which is the angular speed or angular velocity. Angular motion also have a direction. We talked about this before. If you have the omega, then counterclockwise is positive, clockwise is negative. That's how we kind of define the direction of the rotation. Okay, now I'm going to derive this one, why you can write I omega squared. We're going to start from this one here. Okay, So 1/2 mv squared. So 1/2 mv squared. Well, what is the velocity? Well, we just tell you the velocity of this motion is equal to r omega s squared. So then I can write this one as 1/2 m r squared omega squared. Now omega doesn't change, it's always going to be a constant. So what I mean is, if you have several pieces as moving at the same time, then I have 1/2 summation of mi ri squared multiplied with the omega squared. And what is this? This is what we define as the moment of inertia. And that's why we can use this equation to represent that. So as long as the I is composed by several elements, then you can always use this way to find the rotational kinetic energy. Again, omega is not going to change for a whole body, and therefore the omega is going to be constant. However, the I will be the summation of each one of the element with the mass and also distance away from the center. Then you can calculate the rotational kinetic energy. Just be careful, the energy has the unit of joule. So for both of the kinetic energy, the unit is going to be joule. And that's simply just equal to, this will be your Newton times meter. And that is the joule. Okay, so if I go back to here, can we also calculate the energy for each one case? Well, certainly you could. If you use the equation, then you simply just use the equation, the kinetic energy of the rotation is equal to 1/2 I and the omega squared. If I know the omega, which we didn't given with the omega, but if you know the omega, then you can use this equation to find out. And notice omega doesn't change, right? The speed doesn't change. However, if I change, kinetic energy will change. All right. The next thing we want to talk about is what happens if you are not only have the rotation or you not only have the translational motion. If you have both, kind of motion, how do you do the calculation? How do you find the relationship between the kinetic energy and the rest of the energy? Well, this is going to be expanded from our previous discussion about the chapter 6. When we talk about the energy, then we can extend this to include the rotational motion. So this is the general form because you could have a work done to the system if the work done by the system is non-conservative force, like a friction, or applied force. So here, one way to write this equation is you put all the kinetic energy initial and the potential energy initial, and you add with the work that will be equal to the final kinetic energy plus the final potential energy. Well, this K here represents the total motion kinetic energy, and that including the translational and the rotational, and which means the K could have two different things. If you have an object doing the same kind of a motion or two different motion at the same time, how could you have these things happening? Well, this actually is the most common kind of a motion. Let's think about this way. Just make a drawing here to show you kind of a different kind of motion. Now, if you are driving a car here, this is a car. And there's a wheel over here. The car is going to move in this direction. Let's say car is moving with this direction. Now, we can calculate the translational motion of the car by simply assuming everything is moving to the right, and then you simply use 1/2 mv squared. Okay. But if you look at the tire, if you look at one of the tire, so this is one of the tire. What is the motion of the tire? Well, the motion of the tire is the tire is going to move forward, it's going to move along the line. At the same time, it's going to rotate when you're driving a car. So the tire itself actually has a motion go this way, and it also have a motion going this way. So it's a combination of the translation and also the rotation. Let's say this is the translation motion, which represent the mass. The center of the mass is moving horizontally along the line, and with the v sub cm, which is the center of the mass velocity. At the same time, you have omega. This omega is how the tire is rotating. So if this is the case, then you cannot simply just use translational motion kinetic energy. You also has to add with the rotational kinetic energy, and where the I sub cm is going to be what? If the tire can be simulated as the disk, then your I is going to be the I of the disk, and is rotating about is rotating about a circle, the center of the circle. Okay, so center of the disk. It's not doing like rotating about the midpoint of the tire. Okay, so you have to know how to get this one here. Well, if you look at the table that we give the textbook, the table 8.1, and what is the situation? Well, this one is the situation that you're looking at. So you simply make the rod to be smaller, thinner, and it doesn't change the equation. It will change the mass, but it's not going to change the rest of the thing. And then you simply use this equation to find out. So this I will be 1/2 mr squared. The n is going to be the total mass, and the r is the distance from here to here. So that will be your r. Okay, so but when you do this calculation, the first thing, and a lot of time, the question is, how do you find the velocity if you have a translational motion? Or if you have a rotational motion, then how do you find omega? Now, and just like what we were saying, there is an equation that you can use. If you know the translational motion velocity, then you can find out the omega by using this equation. Or if you find out the omega, you can also find v sub t if you know the radius. This r simply represents the distance from the center of the rotation. Okay, so we're giving you this example here to show you how you find the v sub t, because it's the one that you're going to use as the translational energy. This example, you have the turbine blade rotating with 25 round per minute, or revolution per minute. We want to see how fast of the speed at the point that we pointed at here in the figure. So you have a point at which is 0.5 meter away. You have another point which is 1 meter away. Are they going to have the same speed? Are they going to have the same angular speed? Well, they are going to have the same angular speed, but they are not going to have the same tangential speed. The tangential speed will be different because the tangential speed depends on the r and omega. R is going to be different. So for this case, if you want to find this, then the first thing you have to deal with is actually you have to change the unit of this one here. The omega is 25 round or revolution per minute. We want to change this one to radian per second. So if you wanted to use the SI unit system, you have to change to a radian per second. I know one round or one revolution is 2 pi radius. I also know that 1 minute is equal to 60 seconds. So if you multiply all these together, you're going to get the result of this, which is, let me see. Okay, so that will be 2.62 radian per second. And if you want to find the velocity at the first point, that's simply just equal to R1 times omega, where R1 is 0.5 meter multiplied with 2.62 radian per second, and you got 1.41, 1.31, sorry, radian. And that would be not radian per second, that would be a meter per second. And similarly, you got V sub 2, which is R2 omega, and this time is going to be 1.0 meter, 2.62 radian per second. That will give you 2.62 meter per second. Okay, so that's how you can use this information to find the speed at a different point of this object. Okay. That's give you one example to show you how to use the conservation of energy to do a calculation with an object that has two different kind of a motion together. I need to fix this one a little bit. So there's no such thing here. There's no such thing here. Should be. Okay, so here, here is what happened. We have an object which is a cylinder, a solid cylinder. So if you look at this object actually looks like this. It's a solid cylinder. And it's rolling along a slope, the incline surface, a ramp. And it's going to tell you it starts to rotate without any of the slipping. If an object slip, that means there's a friction. So because there's no friction, well, yeah, if it slip, then you have to consider about the kinetic friction, and the rotation is not going to happen. When it slip, everything is going to slip at the same time, then you don't have a rotation. And because it says there's no slipping, there's only like this rotation, then you need to consider about the rotation in this case. The R is phi. The distance of this one here is 2 meters. The angle over here is 25 degrees. And we want to find out what happened if this one rolls down to here. When you roll down to here, we want to find out what is the speed of this cylinder when you roll down to the ground. Okay, so we want to find the speed. So this one, we're going to use the energy method because this is related to the conservation of energy. Now, because there's no friction, we don't need to consider about the work of the non-conservative. The only thing that we have, if you look back what the equation that we give you before, this is the equation. So we have the kinetic energy, potential energy, plus non-conservative force work, and then equal to final kinetic and potential. So initial equal to final. That's it. So you sum all these together, then the value doesn't going to change. Whenever you use the working energy method, you always wanted to point out two different states. So this is a state 1, this is going to be state 2. And then you're going to collect the information to describe the different state. Now, at the first state, we know the initial velocity is equal to what? Well, start from rest, so that would be 0. What about the omega I? What about the rotational speed of this one at the beginning? It's going to be 0 because it starts at the rest. It's not rotating, it's not rolling down. So that both of the things is going to be equal to 0. And then what about the final? Well, the final, you're going to have V sub f, you are also going to have omega f as well. Okay, now what else? You can see there's a high difference. So what is the high difference is going to tell you? It's going to tell you, well, when this one roll down, you are going to drop certain high. This is going to be the drop of the high. And how much is the high drop? And then you look at this triangle here. This is a triangle with the degree of 25 degrees. This is the high drop. If you make this one to be 0, and then this high of this object is equal to h, where we know the h is equal to the hypotenuse times the sine 25 degrees. So it's going to be 2 times sine and 25 degrees. That's your change of the height. Okay, once we have all this information, then we can start to make a table which will help us to solve this problem. I'm going to create a table here. Let's create a table, and we start with the state. And then I'm going to look at two different kinetic energy of the translational. I also have a kinetic energy of the rotational. And then I probably will have a potential energy. In this case, we only have a gravitational potential energy. So these are the energy happen in each one of the state. Here is state 1, here is the state 2. So what is the kinetic energy of translational for the state 1? Well, Vi equals 0, so this should be 0. What about the rotational kinetic energy? It's also going to be 0 because omega I is equal to 0. What about the potential energy? Well, the potential energy is mg times the high. So this one, if we make the bottom to be 0, this will be mg h final. Or you can simply just say this is the h, right? That's the high difference. Let me just use high. And then let's look at the second state. Well, at the second state, it's going to have a velocity, and I don't know what a velocity is. Actually, that is the thing that we try to find out. What about rotation? Well, it certainly is also going to rotate, and this will be not the m, but the I times omega squared. Are there any potential energy? No, because we're going to set a bottom to be the reference point, so there's a 0 of the potential energy. You can see this kind of table is going to tell you the object, the cylinder, actually change its potential energy, gravitational potential energy, into two different kind of kinetic energy. One is rotation, the other one is translation. And the way to find a solution is simply just look at these two and see what other value that is given. Now we are given with the, do we given with the mass? Yes, the mass is equal to 3.00 kilogram. So I can simply just write the M 3 kilogram times 9.81 meter per second squared times the H. How do we know the H? The H is 2 sine 25 degree. 2 meter times sine 25 degree. So that will be my potential energy for the state 1. What about state 2? Well, the state 2, I have 1/2 M at 3 kilogram. What is the V sub F? I don't know. This is something we try to find out. Let's just write down the V sub F squared. And what about the second one? The second one is 1/2 I omega F squared. So what is I in this case? Then you go back to look at the table that is equal to 1/2 mR squared. What is M? That's 3 kilogram. What is the R? R is the radius of this cylinder, which is the big R, which is a 5 centimeter. And I need to convert it into the meters such that our calculation will be consistent with the same unit system. Okay. So that should be square. Okay. Wait, so yeah, so this is an inertia, right? What else? 1/2 I omega squared. So I also need to put omega F squared. Well, if you look at here, and everything kind of a known except the only thing we don't know is the V sub F and omega F. That means you have two different things that you don't know. You make the equation 1 equal to equation 2. If you calculate this one here, this one will give you 24.88 joule. The second one here is complicated because there's something that we don't know. Then how do we find out the solution? Well, you have to use another equation that we emphasized this one before. The V, the tangential direction velocity is equal to the R plus omega. So if you want to find the final velocity of the object, it's going to be equal to R omega final as well. So we can replace, either replace the VF equal to R omega F squared, RF, and take the square of this, or we can change omega F into VT over R. I'm going to try to solve it for the omega by simply just this one to replace this one here. So you use the VF equal to R omega F squared. You can replace the omega and the V sub F. If you do that, you will find out the omega in this case is going to be 66.5 radian per second. But the problem is asking us about the V sub F. So how do you find the V sub F? Well, V sub F is equal to R times omega. And what is R? The R is simply just 0.05 centimeter times your omega F, which is 66.5 radian per second. And then you will find out the V sub F, that will be 3.33 meter per second. Okay, so this is the way that you can use kinetic energy method to find a solution. And remember to make a table which can help you to organize the information and also help you to find a solution in this case. In this case, we are using the potential energy and change that into a kinetic energy, or the kinetic energy composed by rotation and also the translation. Okay, don't forget about the translation. People only think about, whoa, this is rotating, so I only have a rotational energy. No, it's also moving forward. So you will also have a kinetic energy as well.